Biraz dışarıdan gelen sesleri bastırması için bir küçük bir müzik şey yaptım. Yani ritmini de almaması için. Okay, let's start. We have 27 students here. Okay, so let's recall what we were doing last week. Okay, so last week we were studying this section 4.3, which is about subspaces. Okay, so we were discussing vector spaces. So vector spaces are structures which are sets basically with some operations. There are two operations. One of them is vector addition and the other is scalar multiplication. And they satisfy certain properties, okay? There were 10 properties. So those properties really resemble the usual vectors on the plane and in the space, okay? So you know the usual vectors, so that's basically the same structure. Okay, then we talked about subspaces. So if, let's say if V is a vector space, okay, vector space, then we look at a subset of V, okay? So you remember this symbol means subset, right? So this means subset. If W is a subset and W is also a vector space, then we call, so let's say V space, okay, instead of vector space, then we call W a subspace, okay? Any questions here? Okay, then we said you don't need to check all those properties to verify that a given subset is a subspace. You need only check two properties, okay? This was a theorem which says that W is a subspace. So this is just a reminder from last week. W is a subspace if two conditions are verified. So if the first one, we call it A. So for all the vectors in the big space W, okay, so these are the vectors, okay. So we want V plus W to be in capital W, okay, if this is the first condition. So which means if you add the things in W, the smaller set, you should remain in W to be a subspace, okay. So the second condition was about the scalar product. So I hope you know what this symbol means. What does this symbol mean? This symbol means for all, for every possible. So maybe I should write for all instead of that, okay? Anyway, and here for all scalars C, okay, our scalars is real numbers, remember. And for all vectors in W, what do you want? You want C times V to be still in W, okay? So if you multiply, if you take scalar product of vectors in W, you want them to remain in W to be a subspace, okay? Then, okay, we said that every vector space has two trivial subspaces. One of them is the zero subspace, which is consisting of only the zero vector, and the other one is the whole space, okay? I'm not going to talk about all those details, and to visualize what is a subspace and what is not a subspace, for example, for example, we did an example like this. Let me try to make this bigger. So we took R2, the plane. Okay. So we looked at, for example, if you remember, we look at oops. We look at right portion of this plane. So we ask the question whether this part is a subspace of R2, okay? Whether the right portion of R2 is the plane, is a subspace. Then we said, okay, so what should be verified is these two conditions, okay? So if these two conditions are verified, then this blue part is a subspace of R2. And then we show that they are not satisfied. The first condition is satisfied. Why? Because if you add two vectors, if you add two vectors here, let's take a vector here, like this, okay? Let's take another vector, I don't know, like this. And if you add them, you see that the result is this guy, right? So if you add vectors in the blue part, they still remain in the blue part, okay? So by the way, how do we, so let's be more formal. So V is, let me choose blue color. So V is R2. What is R2? R2 is the set of all vectors of this form, first component, and B second component, okay? So, and what is W? W in this case is the vectors of this form, A and B, but we have a constraint on B, which is B is, let's say, greater than or equal to 0. Okay? So the question is whether W is a subspace of V. Is W a subspace? The question is this, right? So we have to verify those two conditions. So if you look at it, the first condition is satisfied, but if you look at the second condition, it won't be satisfied, right? Because if we multiply this red vector by, say, -1, it will go to the other direction. So it won't stay in the same set. Okay, any questions here? Hmm? No? Okay, so let's try to, so let me give names to these guys. So this is V, and this purple one is, let's say, W. Then you see V plus W is still a vector in the right part, but if you look at minus V is not in W. Okay, so to be a subspace, it should be in W. So the answer is no. W is not a subspace. Okay, so let me make this bigger. Not a subspace. Okay, this is what we did last week. Okay, any questions? Okay, good. Then we defined something called linear combination, right? So we take some vectors, v1, v2. So we take k of them. So these are vectors in a vector space. And we have some scalars. Let's call them a1, ak. So these are real numbers. Okay. So we don't specify which vector space is V, so it can be any vector space. It can be the vector space of vectors in R2, vectors in R3, vectors in Rn, the vector space of polynomials. Doesn't matter. The definition works for all of them. Okay. Then what did we define? Okay, so our definition was this. Then A1V1, A2V2, okay, we're taking the product of the scalars with vectors plus AKVK. So this what is this result? So this whole sum is still a vector, right? Because I'm multiplying vectors with numbers and then adding them. So the result is still a vector in the same space. And this result is called a linear combination. Let me so this is called a linear combination. So I couldn't fit it here. Anyway, so let me try to move it. Nation, okay. I think this part is now broken. Okay, so this is called a linear combination. Any questions? Okay, then we ask some questions. For example, do I want to do this again? I'm not sure. So yeah, maybe let's give an example. So to remind you, so we took, for example, the question is this: is, for example, 1 and 2, the vector 1 and 2, a linear combination? So instead of linear combination, I will write a linear comp of the vectors. Let's say, I don't know, 2, 3, and 4, 6. Okay. What do you think the answer will be? Okay, here we're talking about vectors in the plane, right? So the question is whether 1, 2 can be written as a linear combination of 2, 3, and 4, 6. Okay, let's look at it. So we are wondering if there exists numbers a and b, or a1, a2, such that a1 times 2, 3, plus b2 times, no, not b2, but maybe a2, 4, 6. So the question is whether this equation has a solution. Has a solution. This is the question. Let's look at it. So what does this mean? This means two equations, right? The first equation is 1, 2a1 plus 4a2. And the second equation is what? 2 equals 3a1 plus 6a2. What do you think? Does this equation have a solution? Can we solve these equations for A1 and A2? Orada mısınız arkadaşlar? No, right? No, we can't. Thank you. Because you see, if I multiply the first equation by 3, I get the left-hand side equals 3. And if I multiply the second equation by 2, I have the left-hand side 4. But the right-hand sides are equal. So these equations cannot be solved. Okay? So one way of seeing this, right? So you can look at it using the standard procedure, which is this one. Okay, so we write a matrix augmented form, and we look whether this system has a solution. So you see, if I do which operation, if I multiply by the first row by minus 3 over 2 and add it to the second row and replace it with the second row, then what do we get? We get 2, 4, 1. And what about this part? This part becomes 0, 0. What is this thing? Minus 3 over 2 plus 2 is 1 over 2. Let's look at the last line. What does the last line say? The last line says 0 times A1 plus 0 times A2, 1/2. So no solution. Okay? There is no solution for this system. So the answer to the question is no. This vector isn't a linear combination of 2, 3, and 4, 6. Let me try to also explain this question geometrically, okay? So let me draw the plane. Okay, so we have the vector 1, 2. So 1, 2 is a vector like this. And what is 2, 3? So this is the vector 1, 2. What is 2, 3? 2, 3 is another vector, right? So I'm not sure about the slope. So slope is slightly slow. So 2, 3 is a vector like this. This is the vector 2, 3. And 4, 6. 4, 6 also lies on the same line with 2, 3, right? It will, how do I make this? So it will lie on the same line. So, oops. This is difficult to draw. So this is 4, 6, okay? So the question is this, can I reach this direction of 1, 2 by using these two directions? And the answer is no. So no matter how I choose A1 and A2, I will always remain on the same line, okay? So these two vectors, 2, 3, and 4, 6, lie on the same line, and if I multiply them by numbers and add them, it will still lay on the same line. So I cannot reach this vector 1, 2. Okay, so this is the geometric idea. Any questions about this? Any questions, guys? No? Okay. Okay, so we have one more example from the last section. Let's talk about it. So this is not just an example, but also like a theorem. So suppose we have a matrix, m by n matrix. And suppose we look at the solution set. the solution set of a times x equals the 0 vector. This is a subspace, okay? The solution set is a subspace. Is a subspace of Rn. I'm not sure if this is an example. This is more like a theorem, okay? Maybe we should call this a theorem. Okay, so what do we mean by this? So why is this a subspace? So the solution set of Ax equals 0. Why is this a subspace of Rn? We need to check two things, okay? Those two things are this. If, so let's write proof. So the proof is this. Remember, to be a subspace, two conditions must be checked. First one is the sum of two vectors must remain in the same set. And the second one is a vector and the product of a vector and a scalar must remain in the same set for all possible combinations. Okay? So if x1 and x2 are two vectors which are solutions, then we need to check that then we should have x1 plus x2 should also be a solution. So what does it mean to be a solution? It means that a times x1 plus x2 should be 0. So is this very satisfied? If we have two solutions, x1 and x2, what do you think? Okay, yes, right, because if you look at it, what is this thing? So this means I can separate this into two parts, like this. So ax1 plus x2, since A is a matrix, we can write it as ax1 plus ax2. And we know that ax1 is 0. Why? Because x1 is a solution. Okay? Solution means it is solving this equation. Okay? x1 is solving this equation. So both of these expressions are 0. So this is the 0 vector plus the 0 vector. So their sum will be the 0 vector, which means the answer to this one is yes. So we verified that if x1 and x2 are solutions of this homogeneous equation, okay, of this equation, then their sum is also a solution. This was the first condition to be a subspace. So let's check the second condition. If x1 is a solution, okay, if x1 is a solution and c is any real number, then the second property is if whether we have a times c times x is 0. So the question is now this. But this is also automatically satisfied, right? Let's see. Let's see. So if you look at it here, this means c times ax. Because I can move the constant out of this operation. So a times x is 0 because, oh no, this is x1. This is x1, okay? A times x1 is 0 vector because x1 is a solution. So this means c times the 0 vector. And if I multiply, if I take the product with the 0 vector, the result is 0 vector. So the answer to the second question is also yes. Okay, this was a theorem. So let's try to give some examples to it, okay? Okay, so let's try to illustrate this example. For example, let's take an easy example, okay? Like this. x1 plus x2. So I don't want to give it a very difficult example. x2 plus x3 equals 0. Let's look at the solution set of this system. What is the solution set of this system? So the solution set, okay, we have two equations, right? Two equations and three unknowns. So I can consider these two guys as leading ones, x1 and x2. So I can solve these in terms of x3, okay? So x3 is a free parameter here. x3 is, let's call this r, so this is free. Then what is x2? x2 is minus r, and what is x1? x1 is minus x2, which is r. Okay, so what does this mean? This means, let me try to make this bigger. So this means x1, x2, and x3 are given by this. x1 is r, x2 is minus r, x3 is r. So this is the solution set. Solution set. Okay, so this is also a subspace, guys. Okay, by the above theorem, this is also a subspace. Why? Because if I take two such vectors and add them, the result will still be a vector of this form. Okay, for example, if I add 1 minus 1 1 and 2 minus 2 2, the result will be 3 minus 3 3. Okay, so whatever I choose r, if I take such two vectors, the result is the sum of two vectors is still of the same form. Okay, and if I take such a vector and take its product with the scalar, the result is still this like same form. So this is really a subspace. Subspace of which vector space? So this is subspace of R3, right? Three-dimensional vectors, because it has three components. Any questions here? Okay. Arka planımı nasıl buldunuz arkadaşlar? Güzel değil mi? Bugün değişik bir yerden anlatayım dersi dedim. Geçen haftalarda biliyorsunuz uzaydan anlatıyordum dersi. Belki öbür ders başka bir şey koyarım. Ayder Yaylası güzel fotoğraf varsa gönder Mustafa Yanar. Link gönder. Link gönderebiliyor musun orada? Tamam, gelecek ders Ayder Yaylası olsun. Hatta birkaç koyun falan varsa koyun falan da olsun şöyle arkada. Tamam, her ders önerilerinizi gönderin arkadaşlar. Gelecek derste önerilerinizi de şey yapacağım. Evet, bugün katılım biraz daha yüksek. Herhalde yoklama alacağız diye mi ne oldu arkadaşlar? 40 kişi, 30 kişiye düşmüştük. Evet, bu konular biraz teorik arkadaşlar. Ama anlarsınız o kadar da teorik değil. Yani teorik olan şeyleri anlayınca pratik oluyor. Öyle diyeyim. Bilmiyorum anlamlı mı bu söylediğim ama. Okay. If you don't have any questions, I will move to the next section. The next section is 4.4. So this is about span. Span means, in Turkish, it means germek. Okay. Okay, so let me give a definition. So, so if we have, so we always start with the vector space, okay, vector space. And we have some vectors in that space. Let's call them v1, v2, and vk. So these are vectors in this vector space. This vector space can be anything. Okay, and if we take some, okay, let me write the definition. The set of all possible linear combinations, all possible linear combinations of these vectors is called what? It's called the span of these vectors. Okay. Tamam Mustafa'ya da öbür ders bakacağım. The span of V1 to Vk. Okay, so let's give an example. Okay, so the question is, let's try to find the span of I don't know. Let's take two vectors, okay? 1, 2, and I don't know. Let's take 0, 1. Okay. Let's find the. So these are vectors in R2, vectors in the plane. So for this one, we're considering. So span means. So all linear combinations, right? All linear combinations. A1 times the first vector plus A2 times the second vector. Okay, so these are A1 plus 2A1 plus A2. Okay, so you see, now any vector in R2 can be written like this. What do I mean by this? What do I mean by this? I mean this, if I take any vector, x and y, then for some A1 and A2, these will be, there will exist A1 and A2 such that it gives this one, right? So if I choose x to be A1 and what do I want to do? No, if I choose A1 to be x, I want to go backwards. if I choose A1 to be X and A2 to be Y minus 2X, then I can express any XY using these two vectors. Okay, so the span of 1, 2 and 0, 1 is R2. Okay, so to what I said here, let me give an example. For example, if I take 3 and 5, then 3 and 5, any arbitrary vector. Okay, I'm trying to illustrate what I said. So I can write this as a linear combination of 1, 2, and 0, 1. How can I do that? So I can first multiply the first vector by 3. Okay, so if I have this, I get 3 and 6. Now I get so what do I need to do? I have to multiply this by -1 times 0, 1. So you see this equation is satisfied, right? So what does this mean? This means 3, 5 can be reached by a linear combination of these two vectors, 1, 2, and 0, 1. Okay, so if I move 3 units in this direction and -1 unit in this direction, I get to this vector, meaning that 3 and 5 is a linear combination of these two vectors. Okay. This is not true for just 3 and 5. This is true for any x and y. Okay, what we said is true for any x and y. So any vector in R2 can be obtained by these two vectors 1, 2, and 0, 1. This means the span of these two vectors 1, 2, and 0, 1 is every vector, every possible vector in R2. Okay, it's okay for me. I hope it's okay for you as well. So let me draw what I said here. So let me choose a smaller one. Okay, so I said 3, 5, right? So 3, 5. What is this 3, 5 vector? 3, 5 vector is something like this, right? So 3, 5 vector is this. So what I said is if I move, so what is 1, 2 vector? 1, 2 vector is it steeper? No, it's 3, 5. Which one is steeper, guys? 2, 1 is steeper, right? Yeah. So 2, 1 is something like this. Wait a minute. Oh yeah, I understand now. Okay, let me make this a little bit smaller. Okay, so this is the vector 1, 2. So if I go 3 times like this, of course, this is a picture. I won't be too good at it. And then move -1 times in the direction of 0, 1. I get to this green vector, right? That's what it says. So this is 3, 5. This purple is no, pink. This is pink. 3 times what is this? 3 times 1, 2, right? And what is this orange? Orange is -1 times 0, 1. Okay. So I illustrated this for 3, 5, but this is true for any xy. Okay. Now let's go back to the other example. So let's look at still we are in we're still in R2. Let's look at this case. So find the span of let's say 1, 2, and 2, 4. Let's look at the span of these two vectors. Now, what does span mean? Span means, again, all linear combinations of these two vectors. Okay, so I have to write a1 times the first vector plus a2 times the second vector. So if I look at it, what do I get? I get a1 plus 2a2 and 2a1 plus 4a2. Okay, so you see there's a relation between these two coefficients now. The second component, this part, is 2 times the first component. So I can only reach vectors whose second component is 2 times twice the first component. I cannot reach the other vectors, okay? For example, 3 and 5 is not in this span because 3 and 5 is not 2 times 3. So I cannot write 3, 5 in this form. Okay, I can write 3, 6, but 3, 5 cannot be written. Okay, so I can, let me show you one more thing. So I can write this as a1 times 2a2 times the vector 1 and 2. Okay, so what this really means is the vectors in the span is really a multiple of this vector 1 and 2. Okay, you can see it. 1 and 2 is a multiple, and 2 and 4 is a multiple, and any linear combination of them will still be a multiple of 1, 2. So the span of this, let me draw it. So the span of this thing is so the span of this guy will be what? What is 1, 2? 1, 2 is this vector, right? So this is the vector 1, 2. So 1, 2, and 4, 2, 4. And 2, 4 is still on the same line, so it's double the length. So if I take the linear combination of these two vectors, the linear combination will always remain on this line. So it won't go anywhere else, okay? So the linear combination is really a line. Linear combination of 1, 2, and 2, 4 is a line in R2. So this is the linear combination. In the direction 1 and 2. Any questions, guys? So in the first example, these two vectors can reach anywhere. The first example, okay, this one. Let me close this. 1, 2, and 0, 1 can reach anywhere in this plane. But 1, 2, and 2, for using these two vectors, you can only reach vectors on this line, okay? So the span of these two vectors is this line, and the span of 1, 2, and 0, 1 is the whole plane. That's the difference between these two cases, two examples. Any questions? Okay, let's give a small break, okay? Let me turn this off.